Thank you, Murat. Today I want to talk about, can you hear me? Okay. The motion of axisymmetric magnetic eddies with swirl. And here we have a little background from astrophysical fluid dynamics. And in the sun, the surface of the sun, we have magnetic loops like this. Much more beautiful pictures were introduced by Hornig yesterday. And these magnetic loops is a bundle of magnetic fields, and the reconnection of these magnetic loops heats the solar corona to extremely high temperature. And this magnetic flux tube is regarded here as a magnetic eddy. The magnetic fields and vorticity fields are concentrated in these loops. And including this magnetic loop, coherent structures in magnetic hydrodynamics, MHD, can have a key role in generally in astrophysical fluid dynamics and plasma physics. And by the way, in ideal MHD, we have some invariants which include total energy and magnetic helicity and cross helicity. And we have topological background. So this is a symposium of topological fluid dynamics, and this is helicities bound energy. Helicity give bound for energy. So in MHD, magnetic helicity is conserved, as I said, and this bounds energy and magnetic energy from below. So we have this inequality by Poincare inequality. So if magnetic helicity is non-zero, magnetic helicity cannot decay to zero. And we have also cross helicity conservation, and this cross helicity also give bounds for hydrodynamic energy and magnetic energy. So from Shart's inequality, we have this inequality. It is some kind of bad notation. Both energies are bounded by this two bounds, so these must be in this interval. And for the dynamics of magnetic eddy, I did some work with Keith Moffat several years ago. So in this work, we considered axisymmetric ideal MHD, and we considered the velocity field only have a poloidal component, and the magnetic field consists only of toroidal component. And we found a family of exact solutions which include Hill's spherical vortex as a limiting case. And we found a formulation by contour dynamics under this assumption, and we did numerical simulation using the contour dynamics. And we found that starting from a certain type of initial condition, the exact solution we found is actually formed in the simulation like this. So in this part is well described by the exact solution we found. And we found that this part keeps finite amount of magnetic energy, and magnetic energy cannot decay to zero. And from the topological background, in this situation, the both helicities are zero, and the inequalities are trivial. So these are zero, and this intervals is trivial also. So there is no constraint about the energy. But in spite of these facts, the energy, magnetic energy, cannot decay to zero. And in this work, there is a limitation, another limitation. Vorticity inside the eddy is assumed to be zero. So in the present study, we consider dynamics of magnetic eddies which have swirl. And by putting swirl, we have non-zero cross helicity in general. Magnetic helicity is still zero, unfortunately, but we can consider how does the cross helicity constrain the dynamics by this formulation I show in the next slide. And we are also interested in the effects of vorticity inside the eddy. And in doing these with these objectives, we use quantum dynamic simulation. And quantum dynamic simulation has two advantages. It can simulate ideal flow, so flow without dissipation. Invariants are conserved numerically. So this is not the case for many finite difference method or spectral method and other methods. And the other advantage is by this simulation, we can reduce spatial dimension, essential spatial dimension. We have an axisymmetric flow, so this is in essentially 2 dimensions, but we just track the contour, which is a one-dimensional object, so we can reduce the spatial dimension, and it's quite efficient. And this work is, of course, the extension of my work with Keith. So the settings are summarized in this slide. We consider incompressible MHD flow, and we assume axisymmetry, and no dissipation is present. And we assume magnetic field has only toroidal component, but now we have velocity field, both toroidal and poloidal components. And in particular, we consider this type of flow. This is a cross-section including the axis of symmetry. And in this section, we consider a finite region denoted by D. And inside D, we have a toroidal component of magnetic field and velocity field assumed to be in this form. So the magnetic field is proportional to R, the distance from the axis of symmetry, and the velocity is inversely proportional to R. And outside of this region, both components are assumed to be 0. So the governing equations are the normal one for MHD. We have Euler equations, which has a Lorentz force term, and incompressibility is assumed. And Maxwell equations with MHD approximation, we have this equation. And by the assumption we have now, these equations becomes like this. Important point is both equations for toroidal components reduce to this equation. So F describes the boundary of D. F equals 0 describes the boundary of D. So this equation becomes reduced to this because outside the D, we don't have any field, and it is conserved along the particle path. And inside D, this is constant. So we just need to track the contour. Yes?
Is there a simple physical situation which is modeled by this addition of swirling?
Well, we believe this is a model of axisymmetric magnetic eddy, but so we can't say we have this distribution in a particular example, but as I show later, this formulation can be extended to multiple contours, and that approximates continuous distribution. So this formulation can be generalized a little. Yes. And for the other component of velocity, a vorticity equation can be derived like this. So it has a delta function on the boundary, which is non-zero at the boundary. And this is a peculiar vorticity equation, which tells us vorticity component is created due to the Lorentz force and the centrifugal force. So the strength of the vortex sheet varies with time. So to summarize, we consider the class of solutions like this. So the vorticity component, theta component, has a vortex sheet on the boundary, and uniform vorticity, actually uniform is omega theta divided by r inside D, and outside we have only all components at 0. And u theta and b theta are also given by Heaviside function. Then what we have to do is solve this equation. So the details are not important. We just need to track the contour parameterized by s, and time t is the time, and the strength of vortex sheet gamma. Actually, this is not the strength, but related to the strength. So strength is a gamma, and because the vorticity induces velocity, and their contribution have two components. So UR and UZ comes from the vortex sheet, and U omega R and U omega Z comes from the vorticity inside the eddy. Anyway, we have a Green's function, so we can compute. And the important thing is everything is calculated on the contour integral. So yes, we just need to integrate on the contour. And some numerical techniques are required, because in the vortex sheet, singularities can develop. So we need some regularization to simulate the dynamics with sufficient time. So we introduce parameter epsilon regularization parameter to here. So this one, 5 minutes. Okay. Okay. So then I will be quick. And remeshing is also introduced. So we discretize the contour with this point, and the point distance becomes too sparse or too dense. So we use remesh. So from here I show the results. But before it, it has a basic mechanism. So we have two forces. One is a centrifugal force due to swirl, and the other is a Lorentz force, and it induces magnetic tension. And the resulting force is a restoring force, and we have an equilibrium radius at which these forces balance. So this is an example of the evolution of the eddies. We are seeing the contour in this area, and starting from the equilibrium radius, it just splits into two rings, and it propagates along this radius. And starting off the equilibrium radius, it tends to close to this equilibrium radius, and then these structures propagate along this. And how about the energy? So here we have plotted the total energy and hydrodynamic energy and magnetic energy, and this is a toroidal part of hydrodynamic energy. And this shaded region corresponds to the range of hydrodynamic energy and magnetic energy determined by the cross helicity. So the initial conditions happen to close to the bounds, but it decreases or increases and away from the boundary as time proceeds. And for this case, starting from the equilibrium radius, this is almost unchanged. And the next is the results about effects of vorticity inside the eddy. Here we have set the magnitude of vorticity inside the eddy constant and changed the magnitude of the forces, which magnetic force and centrifugal force. So this case corresponds to the classical vortex ring, and the propagation speed of the vortex ring is well in agreement with classical formula for speed of vortex ring. And if we add these forces, if the forces are weak, it still propagates as a single eddy. But the deformation of the contour is quite evident. And as the forces become strong, it tends to split into two rings like this. But after the split, these structures formed a head and top and bottom looks like quite steady. So we seek a steady solution by perturbation expansion. And this is only a result. So the resulting steady solution is inside the core we have a 2D rigid body rotation at the first order. And outside the core we have a 2D potential flow around rotating circular cylinder. And this rotation parameter is different in general because we admit a vortex sheet. But if total circulation is 0, it is total circulation of the vortex sheet is conserved. So initially it is 0, it remains 0. So if the total circulation is 0, this A over 2 and beta must be equal. And from this relation, we have a radius of the ring must be different from the equilibrium radius by this parameter. And finally, we checked the steady solution by numerical simulation. So in this case, we don't have a deviation, and we put initial distribution of vortex sheet. Magnitude of vortex sheet is non-zero initially. So this is the difference from the previous results. And the most part is steadily propagating, but as in our previous simulation, some kind of instability, which resembles the instability seen in the rear of the Hughes vortex, is also formed. And but as a whole, it propagates with speed predicted by the solution. And here we have a structure which actually propagates off the equilibrium radius. And this deviation is also explained by introducing the Magnus force, which exists when the things are rotating. So to summarize, we consider the motion of axisymmetric magnetic eddies with swirl, and we developed contour dynamics formulation, and we consider the relation of the cross-hasty bounds for energy and the motion. And the bounds for energy correspond to the restoring force at equilibrium radius, so everything goes to this radius. And the effects of vorticity inside the eddy, we have when the forces are weak, eddy persists with a single structure, and when the forces become strong, eddy splits into two rings. And we explained the structures appear in the simulations by steady solution obtained by perturbation expansion. Okay, I stop here. Thank you very much.
Thank you very much.
Questions? Andrew?
How sensitive are your results to the smoothing parameter epsilon?
Epsilon.
Yeah, the smoothing parameter.
Epsilon. Epsilon. I didn't explain, but it is the ratio of the core radius to the ring radius. So we have a torus. So the radius of
Better
the
the parameter in the vortex sheet formulation.
vortex sheet.
Formula.
Different.
No,
So,
no.
sorry. That's confusing. So different parameters. Sorry.
Yeah.
You're right. Okay.
Is it sensitive to that though?
The
It's
question-
Yeah. And yes, so the roll-up you saw in the simulation is a result of the regularization, and particular structure is quite depend on the parameter, unfortunately. So we reduce the regularization parameter. We have a fine structure, more fine structure. Yes, more fine structure.
Please, Rasha.
Just a comment. I think perhaps in this kind of scenario you should use toroidal coordinate instead of cylindrical coordinates. It seems more natural.
Sorry.
Say it again. What coordinates?
Toroidal coordinates.
Oil coordinate.
Toroidal.
Toroidal coordinates.
Maybe, but we don't have any.
There is no torus left. It
It
starts
goes like
off with
this.
a torus, but it disintegrates into. Any more questions or comments? I find fascinating that this can be reduced to a contour dynamics problem.
And to answer Dr. Tokeda's question, I just show this. So this formulation is generalized to multiple contours case. So we did simulation with multiple contour case in the this paper. Yes.
Because the Lorentz force
Yes.
is potential everywhere.
Potential.
And the only effect is the jump in magnetic
yeah,
pressure
yeah.
on the boundary.
Yes. Because we are considering the axisymmetric with only toroidal component. Yeah.
Okay, thank you very much.